What if I told you that one of the most common coding interview problems out there is actually just a famous mathematical sequence in disguise? Well, today, we're going to pull back the curtain on the climbing stairs problem and uncover the secret pattern that's been hiding in plain sight all along. So, picture this. You're standing at the bottom of a staircase. To get to the top, you can only do two things. Take a normal single step, or you can take a big leap of two steps. The question is, how many different ways, how many unique combinations of those moves can get you all the way to the top? All right, let's put that a little more formally, just so we're all on the same page. We're given a staircase with some number of steps. We'll call it n. Our only allowed moves are climbing one step or two steps at a time. The goal? We need to find the total number of distinct ways to land exactly on that final nth step. Now, the best way to crack a problem like this isn't to jump straight to some complicated formula. Nah, let's just roll up our sleeves and start small. We'll look at a few tiny staircases and see if we can build up some intuition from the ground up. Okay, let's start with a super simple two-step staircase. How can we get to the top? Well, we could take two little steps, right? A one step, then another one step. Or we could just take one big two-step leap. And that's it. That gives us a total of two unique ways. All right, let's bump it up to a three-step staircase. We could do three single steps, 1, 1, 1. We could do a single step, then a double step, or we could start with the double step and finish with a single. That gives us three different paths. And notice, the order is super important here. Taking a one-step, then a two-step is a completely different journey than a two-step, then a one-step. Okay, so let's get our findings organized. For 0 steps, well, there's one way to do that. Just don't move. You're already there. For one step, there's one way. We just found there are 2 ways for 2 steps and 3 for 3 steps. And if we keep going, you'll find there are 5 ways for 4 steps and 8 ways for 5 steps. Now, take a good look at that second column. 1, 1, 2, 3, 5, 8. Does that sequence of numbers ring any bells? 1, 1, 2, 3, 5, 8. I mean, this pattern shows up absolutely everywhere in nature. You see it in the spirals of a seashell, the branches of a tree, even the petals on a flower. It is, without a doubt, one of the most famous sequences in all of mathematics. And you guessed it, the secret hiding inside this simple staircase puzzle is the Fibonacci sequence. But, just spotting the pattern isn't enough. We need to understand why. Why on earth does climbing stairs produce this famous sequence? Let's dig into the logic. So just as a quick refresher, the Fibonacci sequence is that series where every number is just the sum of the two numbers that came right before it. Traditionally, you kick it off with a 0 and a 1. So 0 plus 1 gives you 1. Then 1 plus 1 gives you 2, 1 plus 2 is 3, and on it goes, creating this beautiful, infinite pattern. Okay, here it is. This is the absolute core of it all, the big aha moment. To get to any step, let's just call it step n, I want you to think about your very last move. How could you have possibly landed on that step? Well, you either took a small one step from the stair right below it at n-1, or you took a big two step from 2 stairs below at n-2, right? There are literally no other options. And that is the connection. It means the total number of ways to get to step n has to be the sum of all the ways you could have possibly reached step n-1 plus all the ways you could have reached step n-2. That rule, that ways n equals ways n-1 plus ways n-2, is the exact same recursive logic that defines the Fibonacci sequence itself. But there's one tiny but super important difference. It's the starting points, what we call the base cases. The standard Fibonacci sequence kicks off with f of 0 being 0. For our stairs problem, the number of ways to be on step 0 is 1, because there's one way to be at the start, by doing nothing. And this little shift in the beginning is the key to everything. So because of that little difference in the starting block, the number of ways to climb n stairs isn't actually the nth Fibonacci number, it's the n plus first one. Our sequence is just the standard Fibonacci sequence, but it's shifted over one position. And that is the final piece of the puzzle that turns this into a solvable problem. So now that we've totally cracked the math behind it, how do we turn this beautiful logic into some actual working code? Let's translate this insight into a solution that's incredibly clean, super efficient, and exactly what you'd want to show in a technical interview. This fantastic method is called bottom-up dynamic programming. We call it bottom up because we literally start at the bottom of the staircase, our base cases, and build our way up to the final answer. Now, instead of keeping a whole list of results, we realize we only ever need the last two values to figure out the next one. So we just use two variables. Let's call them prev2 and prev1. We loop, calculate the current value by adding them, and then just slide our window forward. It's incredibly fast, super efficient, and uses almost no extra memory. Okay, so we've got a fantastic solution. It works, it's efficient, it's great. But in an interview, what really sets you apart is showing that you understand the trade-offs, that you know about other ways to solve it and why you chose this one. So let's compare our method and cover those pro-level moves. Let's look at the menu of options. The simple looping solution we just built, that's the gold standard, the expected answer. It runs in what we call linear time, O of n, and uses constant space, O of 1. You should absolutely never, ever use the simple recursive solution without any optimizations. It just recalculates the same thing over and over and is way too slow. And, for bonus points, you can mention that if n was astronomically huge, there are advanced math tricks like fast doubling that can solve this in logarithmic, or O of log n, time. Now, knowing the answer is half the battle. Knowing the common traps is the other half. People get tripped up by this all the time. Remember that off by one error with the Fibonacci index? Always, always double check your base cases. Remember, ways of 0 is 1. And if you ever even think about writing that simple recursive solution, you have to mention that you'd add memoization, a cache, to make it efficient. So you might be asking, okay, cool puzzle, but why is this specific problem so popular? It's because this problem is the perfect gateway into a really powerful problem-solving paradigm called dynamic programming. That core idea of breaking a problem down by thinking about the last move, that's the fundamental mindset you need to unlock a whole world of much, much harder problems. And with that, I'll leave you with a final thought, which is a classic interview follow-up question. You've now mastered climbing with steps of 1 and 2. So, how would your logic, that ways of n equals ways of n minus 1 plus ways of n minus 2 formula, change if, all of a sudden, you were also allowed to take a step of 3? Once you can answer that, you know you've truly mastered the concept.